Okay, so now I'll talk a little bit about base calling, so you know how how it happens that you get calls, you get sequences from intensities. This is a very hard topic to do research in because the files are really massive, and these days most technologies are erasing the sequences, the intensities, as they convert them into sequences. That's how big and problematic they are. But when they weren't erasing them, we got hold of them and looked at them and found some issues. And I'm going to explain them. They are informative, even if you're not going to do base calling, just to know the kinds of errors you can expect. So I'm going to use genotyping as the application of interest, right? So we're trying to genotype, so AA versus AT. The red and blue colors are going to be used throughout as representing the A allele and the T allele. So there they are. So if you're heterozygous and you're going to have one of each, and when we put you on the sequencer, we're going to put millions of copies of each. Right? So your DNA goes on the sequencer, you'll have millions of copies of both A and B, A allele, B allele, and then we'll have, let's say A and T, and then we're going to have fragments of each, right? So each one of these little pieces, if it's for a certain part of the genome where the SNP is at, you have about the same number of blues and reds. Each one, they're almost identical except for this one SNP. That's what we're looking for. We don't know this exists. We're looking for it. So this is what we saw before, right? So you have that location where you have the differences. Okay, so how does it happen? So here's that location, and you can see that there is the A is a reference, and we have T's. We have enough T's that we might consider this to be a SNP. There's no C's, there's no G's, there's just A's and T's, and this data that I'm showing you actually, if you put it through one of the SNP callers, it says that's a SNP. But this particular data set was from a bacteria that was supposed to be homozygous everywhere. No heterozygous anything. So we know this is a false positive. And now if it's a false positive, how come it's so systematic? It's only T and A. So the first thing we noticed was that, and a lot of people noticed this, is that these errors, these T's that were coming up by error, were towards the end of the read. So this is the same data, but now I have ordered the sequences by where it appears in the read. So in the first one, the supposed SNP is in the first location. We call it the cycle, the first cycle. The name cycle comes from the fact that the machine goes through these cycles, and at each one you get the first read, second read, etc. And there is actually a cycle where the name comes from. But anyways, we call it the cycle. Is basically all it is when we talk here is the location on the read. So then the first read and the second read, the SNP, the supposed SNP is at the supposed SNP location is at the first cycle. The second read is second, and the third is the second, and it's in the fifth, etc. So notice that for cases where the supposed SNP is in the beginning of the read, we never see a T. Right? So you don't get to see a T up until towards the end, and then once we're at the end, we start seeing more T's. So that's just 20 bases, but we can do this. By the way, this is now real data. This is not fake. We can do this with all the reads that map to this location. This was a small little genome, so we could do a lot of coverage. So look at, what is this plot showing us? This is on the x-axis it's the cycle. On the y-axis it's the proportion of A's. Actually, the proportions of A's, T's, C's, and G's. So notice that we get very few C's and G's. So you see how they're all mostly at 0? There's a few that sort of pop out a little bit. We get an error here and there. So that is in agreement with the very small error rate. It's basically close to 0%. But the T's, they, after you're past the 20th cycle, look at what happens. You start getting more T's and less A's. So the problem is that the error, it's not just that you have more errors at the end, it's that the error is systematic. We only get A's. So it looks like a SNP. See the problem? If we have, instead of, if what was happening is that towards the end, we got A, T, C's, and G's, then we wouldn't be here because we would say, oh, that's just error. But because it was only T's, it looks a lot like a SNP. And if we didn't actually bother to make this plot where we're plotting against cycle, we wouldn't have seen this. We would have just seen, oh, there's like 20, 30% T's, maybe not 30, but 20% T's and 80% A's. That might be a SNP, but it's within the binomial error.
Is this limited to Illumina, or can you see it across different platforms?
We see it in solid too, and I can't say for about 450. It's gotten much better since the first data sets we got. That's for sure.
But why the composition of changes along the sequencing cycle?
Why does it get worse towards the end, or why is it just A and T?
No, I mean why along the sequencing cycle the composition will change? Why not just appear at the very beginning?
Why is there no errors at the beginning?
Yeah.
Right. So, I'm going to explain that a little bit soon. Why is it that it happens at the end? The quality of the intensities, it worsens as you move along the cycles. So here's another data. This is a little more data, not just one SNP. And now this is for humans. This is not for a bacteria. This is a similar picture, but what we did is we took all the data. At some point, we downloaded the SNPs being called by the 1,000 Genomes Project, the new SNPs, and whatever they call all the SNPs, also the other SNPs. And we take all the SNPs they call, and we divide it into two groups. The SNPs that they call that are already known, that's in dbSNP. That means it was already in a database, and the ones that are novel. So that I'm only showing you here the ones that were known, the ones that were in dbSNP. And then I'm taking each, then I can go back to the original reads of the 1,000 genomes data, and I can ask, this SNP, this information that tells us this is SNP comes from reads, and I can check for each read where the SNP lives, where on the cycle it was. So every single SNP is in every single read is in some location within the read. So this is a histogram of those locations. Let's see how many there are. That's 15,000. So that's a lot of reads. And it looks pretty flat, which is exactly what we want. We want the SNPs to be equally distributed across the read. It shouldn't matter. The reads don't know it's a SNP. It just reads it, and so that's good. But now look at the novel SNPs. The novel SNPs tend to be, it's common to have novel SNPs coming from the ends of the reads, and that is the sign of false positives. Okay, so see that plot is saying it's more common for a SNP to come from the end of a read than from the beginning. That's not what we want. That looks like they were fooled by this error of the ends of the reads. So what causes this? So we're going to go back to the beginning, where we explain how the technology works, and come back to the images. So for each one of these little circles that you see down there, that's one read. A read will come from each one of those. So you have a location on the piece of whatever it is, glass or silicone, that is lit up, and it's being considered a cluster, a location where there are molecules. And what you're going to do is you're going to take, for each cycle, you're going to take 4 pictures. One picture will light up if it's an A. The second picture if it's a CT, and then a G. So there's 4 pictures per cycle. So that's a lot, right? That's a lot of data. The images are massive here. They're certainly not being kept around. So, and then you have these cycles. So let's look at some actual data. So this is real data from one of the intensity files. And these are the intensity files for the first 10 bases for the first read. Or I don't know if it's the first, but it's a read. Okay, so you have, look at the first base on this read. What is it? It's a T, right? The second one is, look again, C, right? So it's T, C, 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 T, C, and now what? Now look at number 9 is? Okay, you say G, but it could be a T. It's very close. So when you get the read, it doesn't let you know necessarily that it's happened. It does have the quality as a way to tell you. There's one number that comes with each base. There's another number that tells you how sure they are about it. But that's where we are, and that's where we're going to go back to. We're going to go back to this data. It's very hard to get it if you're interested in working on this, but it is possible to get.
Why is there such a difference in magnitude in terms of like in line 1 it's 1,300 and then line 2 it's 6,000.
Yeah, exactly. So he's saying there's a big difference. First we get a 1,300 and then there's a 6,000, where these are all supposed to be the same. So there's both a base effect and there's also a cycle effect, which we'll talk about. These are 10 cycles. 1, 2, 3, 4, 5, 6, 7, 10 cycles, 4 colors.
So cycle represents.
So each cycle is a location on the fragment. All right. So if we were to make pictures of these data, right? So there's 4 colors. So here I'm plotting them against each other in different ways. So the first plot here down here on the left is plotting the A intensities versus the C intensities. This isn't real data, by the way. This is what we would hope it would be like. So you have all the bases are either at that location are either an A, a C, a T. An A, that's the blue. A C, that's the magenta. Or a G or a T, that's the red and green, right? That would be nice if it would look like this, because then there would be no problems calling these. That's what we want it to look like, but it actually looks like this. So this is what the intensity data actually looks like this is for the first read, and it's not that obvious, right? So you have all these, for example, if you look at this one here, you have all this stuff in the middle where it's not going to be clear what you're going to be calling. And especially this one is particularly bad, where in no case, in very few numbers, the A is larger than the C. You see that? This is A versus C, and the A is never larger than the C. The blue are things that got called A by the platform, by the manufacturer. And it's probably right, but it's not obvious. So here are the same pictures as you go down the cycles, and look at how the signal is being lost. You see, it starts kind of like you get high numbers, but as you go down towards the lower cycles, now you have some of these that are basically impossible to call. They're just a mush of points. So, to answer your question, why there's 6,000 and 1,000, it looks like there's just natural variation here. You see how you can get very high numbers, very low numbers? This is, I think, in a log scale. So these will be like 4 times bigger than those. And that is actually coming from there's 2 things that are happening, but one of them is that each fragment has like a fragment effect. Each little fragment forms a cluster and has a different effect. Now within the same cluster, how do we see these big differences? I just think there is still a lot of variability within cluster. Okay, now this is a plot that we still make today. I highly recommend making this plot for any data set. and this is a particularly bad run, but it's quite simple to make. So here's how you make it. You take a few reads. Don't take them all. Take a few, 10,000, 100,000, and you map them to the genome using something that is very liberal, like even maybe something like Smith-Waterman, or if that's too slow, Bowtie, permitting a lot of mismatches. So you can get things that have a lot of errors matching. Once you do that, then you assume that every mismatch to the genome is an error, right? So here what I'm plotting is the proportion of mismatches, and then of each kind, right? So there's, 12 different kinds of errors you can make. A turns into C, T turns into C, A turns into G, T turns into A. So there's every possible error is shown. And in this picture, we already see that A turning to C and T turning to C are more common than the other errors. So that's the systematic error I was talking about. And then there's these spikes, where all of a sudden there's all these errors. So remember, each cycle is a series of pictures. I think that what happens there is that the image somehow went wrong. The whole image got messed up. And at that cycle, you have more errors. So you want to see this to be low. You don't want to see big, like that. You don't want to see big spikes going towards, up towards high levels.
The peaks are different just one cycle, not.
Yeah, so that's at one cycle. That's at cycle looks like 9 or something like that. This isn't that common to see something this bad. So this is like a quality plot that we like making. Okay, so now you know why this is happening, right? We see that somehow something's happening to the intensities. Now we can actually go back and look at them. And here's a picture of this plot, the data that leads to this picture. These are now intensities, not going way back to the intensity files. So this is a plot of A versus T. I have made an MA-like plot. And this is not in the log scale. So it's an MA-like plot where the difference between A and T is plotted on the y-axis and the average of A and T are plotted in the x-axis. But I'm using different colors to distinguish the cycles at the beginning, less than 20, and the cycles after 20, the higher cycles. And you can see what's happening. We know this is supposed to be an A. That's what it's supposed to be. So at the higher cycles, at the lower cycles, the A is in fact higher than the T. That's why it's above 0. Almost all of them. There's a few exceptions, but they're almost all correct. But as the cycles become higher, all of a sudden that sensitivity is lost, and now we have this red mesh. So you can see how we will make a lot of mistakes. All these below 0 are going to be called T's, because the T is bigger than the A. So that's what the base calling problem is turning these things into data, into reads data. And a few papers have been written about that. They're not as common anymore because it's getting harder and harder to do it because the files are so big. We have a paper on it. That's the one I'm going to talk about, but there's other really good ones out there. Base call, that's a good one. We're using their ideas a lot these days. So I'll tell you a little bit about that so you can see how you can use statistical ideas to improve base calling. And so here's the idea. We're just looking at data. We can see that if you plot, this is for one read, you plot intensity versus cycle, now in the log scale. You'll see the problem. The intensity for the signal, right? So why are there two groups? First of all, if you're with me. So there's all the colors are plotted. Why are there two groups? What are those? These are the real ones and these are the wrong ones, right? But you still get intensities for everything. So the first base is a red, whatever that is, A. The second one is a green, blue, right? So these are the bases. There's a read up there. That's the read. And this is the base, this is the background. But you can see that the line, there's a loss of signal, and there's also an increase of background. So for other cases, let me show you another picture. It's not as clean. We're going to get to this in a second, but look at the one at the bottom left. That's going to be much harder to call because the signal and the baseline are very close. So the model that we've been using, we actually have tried to improve the base calling method that exists, is to assume that the observed signal is a mixture of two things. It's either, that's a mixture model in statistics, so the delta tells you it's either 0 or 1. If it's 1, it means you are looking at the correct base. If it's 0, then you're going to look at the other side. So this will be the signal part, and this will be the background part. And the rest of what you see there is the formula for a line. So you have a line that decreases with cycle, and you have at the top, and then you'll have a line that increases with cycle. So the alpha is going to be negative because the signal is going down, and the beta is going to be positive. It's going to be going up. The bigger alpha and the bigger beta, the worse you are, because it means things are getting worse faster. So we can also use those as quality metrics for each read. Now, the other thing that comes from this is for the statisticians in the room. Once you pose a model like this, you can estimate the correct base call by fitting this model. What are you trying to estimate then? If you are trying to do base calling, let's see if you can read a statistical model. In that formula, there are the actual correct calls are up there. Which ones are they? There's not that many statisticians left in the room, but it's the Dill triangles. If this is 1, for C equals A, if I, J, C equals A is 1, that means that's an A. The ith read at the jth cycle, if for base C, if that's 1, then it's called an A. So by estimating those deltas, we will estimate the base call. So, but we can also talk about probabilities of it being each one, and then we'll get a way to have uncertainty for each base. So this is the real data. We fit the model. You can see it fits pretty well, and you get the decreasing signal and the increasing background. And then the other thing you can do is you can estimate the triangle, the deltas, and instead of calling, you can actually report the probabilities for each of the 4 deltas. So in the first read, we have T has about a 90% chance of being true, the 1, and then C, A, and G are very unlikely. So you actually get like a probability profile for each base. And if you look closely, there will be some, like, what's a good example here? Anybody see one where you have 2 letters that are about the same size? 29, right? For 29, no, one a little bit more, no? 30, that's 31. For 31, G and T are almost the same. So what you get from this, if you were to use this, is instead of getting a G call, you say, well, G is most likely, but T is almost as likely. And that would serve like as a quality call. So if you use that to make these calls, you get rid of this problem, kind of. I just wanted to give you a little bit of a flavor of what types of things statisticians could work on with this data. It can get a little bit more complicated than just describing and removing systematic errors. Okay, but I'm going to stop there. And if you have questions, I will take them.